My name is June.
I'm Zachary.
I'm Patrick.
Alright, you guys are group 7.
Number 7.
Team Milkshake.
That's right.
Yeah. Alright, so for the manual portion of the course, how did you implement your controller? Our first idea, we were going to use dual joysticks from an old PTZ controller. That wasn't that cool. So we came up with the brilliant idea of going to Goodwill and getting an actual joystick that we could use, and we luckily had an analog genius on our team who will explain the rest of.
Okay. Yeah, we got ourselves a used joystick that had not only the 4 normal directions, but a whole bunch of switches so we could implement functions, and also the rotational one so that we could implement rotation directly. So we actually we changed. We basically used the original keyboard implementation from the Make controller from Lab 3, except that we changed it so that we only had 3 strings input. One string was 4 analog inputs, one string was 4 digital switches, and the other one was 4 more digital switches. Since we realized that we could combine functions like forward, reverse, and left, right on a single rheostat or potentiometer, since you're not going to go forward and back at the same time. So that way we could free up some of the input and make the response happen a lot faster, since we didn't have to pull the 4th input all the time. So we actually got like theoretically 25% increase in performance, but maybe. So we implemented that. We brought we used like I say, the one analog input had the 4 potentiometers on it, so we were using a polling scheme with the 4 digital outputs so that we would pull one at a time, and so we could get two switches and a potentiometer on every pull. Then when we got into the software, then we implemented the analog version as a 0 to 1023 count, with the neutral position being 512, of course, and a small deadband, so that we would have some stability in flight, so that it wouldn't always be trying to go one way or the other. Then, so then we implemented a 2-stage throttle control in each of the directions, except for the rotation, where we implemented just a on-off because we found that throttle control had no real advantage. Then we also had a sensitivity potentiometer on the joystick, so we implemented that as the top speed governor, so that we actually had in all directions we had a 20% and a whatever the governor said was the top speed. So we actually had 20 to and 40 or 60 or 80 or 100% of speed for best maneuverability for Captain Zach here.
Can it come up with a better name?
No, I was just off the wall, sorry.
Alright, so then how did you approach the autonomous portion?
Well, we thought it was going to be easy at first, because it's just making it go straight and left or something, but it turned out really badly because the sensors didn't work really well. They're not reliable. June and I were really trying to tune the thing with tag detection, but you know, it didn't work out. So what did we end up using? Velocity?
Yeah, so I mean, like Jack said, we basically looked at what sensor data was available and just roughly implemented the autonomous flight using various sensor data, and realized that none of them were super reliable. Like for example, yaw angle turned out to be really accurate in the beginning, but once the drone rotated 90 degrees, and after that, we got to make perfect 90-degree turns, and it just didn't do so with the data that the sensor was giving us. So I think we ended up using the X velocity, which is a forward-back velocity, and we used a discrete integration along with that data to figure out how much we traveled, the ground position, displacement, and then so we know when to turn and stuff like that. And then for turning, we just timed it to make the perfect 90-degree turns.
Yeah, and it turned out that apparently you didn't even have to rotate, but for some reason we were stuck on that idea
that we had to,
and it worked out in the end. So you guys landed right on your starting point, right? Not right on, but it was pretty darn close.
Like half a meter or less or something.
Yeah.
On our second try, we were able to get it to actually go the prescribed path, and do the rotation around the actual poles, and then land was some centimeters away from the starting point.
I was really lucky because
there's a lot of
out on the
external
atrium,
factors.
right, there's a lot of wind, and that throws everything off. Maybe we just hit.
Everyone was having that
Right.
issue. Yeah.
Everyone was having that issue.
With people crowding around, blocked off a lot of wind coming in. It definitely helped.
So the creativity is we took a song and opened it up in Audacity and sampled it for like significant times, and then we made we're making the drone dance precisely to the song. So
you're trying to do some kind of
so exactly. Well, actually, what this is, this opens up a TCP connection. So this acts as a server here, and then the make board opens up a socket, sends a command to play the song. And then it just allows for perfect timing with the drone. So the drone actually knows what time is taking place with the song, so it's actually in time with the
song. In terms of the course, what was the most difficult part of it?
Of the actual class?
Of the actual class.
I think the hardest part of the class was the fact that we had to have such a crash course in C programming at the very beginning. Because, since we were required to take Java for some reason as double E's, and not something useful like C programming, then we have like 1 week to learn almost a quarter's worth to get going on actual embedded processing.
Now, I know some people suggested having 374 as a prereq, but I mean, I'm speaking for myself here, but instead of that, I think having maybe 143 have two options between C version and Java version, for different like CSE and EE people, because then, you still have to take 2 quarters of Java before 374, and we find out, it's kind of useless for EE people. So, I mean, a little bit of both is good, in my opinion, but yeah, they're really geared towards Java in the beginning, and I think that's a huge disadvantage for us.
I didn't think the program was that hard.
I just know how to program so very well. My name's Jack.
No, it's difficult, but it's not as difficult as some people make it out to be. I thought the hardest part was getting set up with Eclipse and everything, because it's so different from what we worked with before.
Right, we're talking about an embedded platform where before we're just programming on a PC and everything works out perfectly because you have all the RAM available and all these resources that are available to you. But when you actually transport that to an actual embedded platform, we're finding out that things didn't want to play as nicely as it normally would just on a PC. But yeah, I didn't think there was anything like crazy hard about the class. I think it was all well done. The idea that the curriculum was made a week beforehand, you would think that might have posed some problems, but everyone was able to shout out the problems that they were having, and it was a really big collaboration on everyone's part, including the professor. So everything got sorted out in the end, and it worked out really well. So it's fun. I'm sure all of us would be lying if we said that the drones didn't make this class so much better. Just being in electrical engineering and especially doing the embedded concentration, it's like right up our alley. So having something fun to play with kind of made all the topics, I felt a lot easier to understand. I felt like I garnered a deeper knowledge of the actual topics because I was able to translate it into a system that was actually interesting to me. Had we made oscilloscopes or just done web servers off of the Make platform, it probably would have still learned the concepts, but it just wouldn't have been as rewarding. The competition setup at the end always drives a lot more effort into at least what I do, the work that I put out. I'm sure you guys could say the same thing. So having the drones there just made everything a lot more fun to do. Like, I don't know if there's any way around that.
Yeah, it
motivated us.
It was definitely nice to have a fun topic in an electrical engineering class instead of just math and stuff like that.
And amplifiers.
All that same old stuff that is good to know, and we find it interesting because we are electrical geeks. But still, it's better to have fun when you're having classes.
like the professor did a good job of setting things up. He's like, these are the topics you're going to learn, these are their applications. So ideally someone would have been able to take that and ported it over to something fun on their own, but having that in front of our face, just him walking in the first day and playing with the drone, it's like, this is what you guys are going to be doing for the quarter, kind of set off the right note right away. So,
you know, we spent hours and hours working on this final project, and having the drone definitely motivated us to, you know, work hard and not be angry about it. And you know, like, the whole competition sort of drove us, you know, to do well and sort of, you know, bring out our full potential, you know, as students, and definitely separating the competition portion from, you know, actual grade. You know, that's fair because, you know, grades should reflect on what we've learned instead of, you know, who won the competition. But he definitely did the whole curriculum well, in my opinion.
I mean, the drones are an embedded platform.
Yeah.
That was the goal of the class, was to provide an intro into embedded systems. The drone had a really nice one available to us. It's a lot better than going and looking at the embedded system of a printer or something to analyze. So
yeah, we haven't spoke with anyone who took 472 previously, but this drone definitely made it more fun, enjoyable. Yeah.